SMT solvers are algorithms that can help us with proving formulas automatically. For instance, imagine you have code like this, and you want to prove that its specification is correct. But before we can prove it, we must first translate it into a mathematical formula. It might look like this. If x is the minimum of a and b, then x is less or equal a and x is less or equal b. It might seem easy to us, but in reality, it's a very difficult task. In just this one simple formula, we already encounter 3 different mathematical theories entangled together. We have arithmetic involving integer numbers, logic with equalities, functions, predicate logic with connectives such as implication or conjunction, arithmetic with inequalities. It's really a lot to deal with. In order to make it simpler, we can substitute the difficult parts with some new variables. Then we plug such formula into a SAT solver. The simplest possible SAT solver might build a table like this one and check all possibilities. A SAT solver does not understand functions or arithmetic, it only understands the logical connectives such as conjunction, disjunction, implication and negation. It can only work with 2 values, true and false. It does not have any concept of numbers or any other data structure. It only checks different truth assignments for individual variables and then evaluates the truth of the entire formula. Here, for example, you can see that the formula may be wrong for certain combinations of variable assignment. Does this mean our specification is wrong? Well, not so fast. So far, we only abstracted all complicated terms with variables, but we are still missing the axioms. To grasp this idea better, first take a look at this squiggly symbol. It's the symbol of semantic entailment. You can read it as, given some assumption x, y holds. For example, consider this simple formula. Every formula may be valid in some semantic models and invalid in some others. A semantic model assigns some value to every variable in the formula. You may think of it as if the formula was some sentence that you say, and semantic model is the context of this sentence. For instance, if I say that it's raining outside, then the time is the context. It might be true today, but it might be false tomorrow. And in the case of our formula, the inequality would be valid in some contexts where x is equal to 1 or x is 0, but it would be false in contexts where x is, for example, 5. Mathematicians, of course, need to have a fancy word for everything, and instead of context, they call it the semantic model. Now, the key part is that we might want to assume certain things as indisputably true. For instance, if we assume that x is greater or equal to 0, then certain semantic models become ruled out. X can no longer be equal -1 or -2 or any other smaller number. We may even make multiple assumptions. If we additionally assume that x is divisible by 2, then we can rule out x equal to 1. That would leave us with only one single semantic model that satisfies our assumptions. And that would be when x equals 0. In such context, we can clearly see that x is less than 2, so the formula is valid. The formula holds in all available semantic models. Quite often, the properties on the left side are called axioms. And this is exactly what we were missing at the very beginning. We used SAT solver to check validity of our specification in all semantic models, but what we really wanted to do is to check whether it's valid only in those semantic models that satisfy our axioms. The only problem is that SAT solvers have no concept of semantic models. They don't understand what an axiom is. We need to find a way to trick the SAT solver into understanding our axioms in some clever way. We humans think in a way that resembles this table. In our minds, we substitute x for different possible numbers and try to estimate what assignments are the correct ones. But SAT solver cannot do this as it would require infinite amount of computation. Instead, we could notice that the semantic entailment works somewhat like logical implication, and the different axioms on the left could be joined together into one large formula using conjunctions. Finally, SAT solver can understand it. However, notice that despite having more axioms, the SAT solver still thinks that this formula can be false. You see, this is perhaps the most important problem when dealing with SAT solvers. It's not just about finding a bunch of axioms, it's about finding the useful ones. Let's go back to the original example. Here I will manually pick the right axioms that should go into SAT solver. You can see that there are quite a lot of them. You probably wonder how I came up with them. The first two are the specification for the minimum function. The next three are the axioms of total order, in particular reflexivity and antisymmetry. The remaining four axioms are for equality. In particular, two axioms encode the property of substitution and the other two stand for transitivity. You can see that it's quite a lot, but at least we've got something that could be plugged into a SAT solver. Each one of those terms will have to be abstracted, that is, we create a new variable for each one of the colored regions. There are a lot of them. You could imagine how huge the resulting logical formula would be, and the assignment table would be even larger. Showing it would be impractical, but just believe me, the table would be true for all assignments, which would mean that the specification is correct. You can see that for us, this job was quite tedious, even though we are a lot smarter than a SAT solver. Just imagine how difficult it would be for a computer to find all those correct axioms. Speaking of which, how do you think? How would a computer even find those axioms? Well, this task goes beyond the capabilities of a SAT solver. It requires help from a special module for quantifier instantiation. You see, usually all axioms would be encoded in form of first-order logic formulas with quantifiers. In our case, it might look like this. Notice how each of those formulas on the left comes from some quantified formula on the right, except that the quantified variables were instantiated. The problem of finding the right instantiations often has no good solution. There only exist some heuristics, and SMT solver tries its best to guess the correct substitution for each quantified variable, but there is no guarantee of success. There are infinitely many candidates for quantifier instantiation. This is why you may sometimes see that SMT solver gives up and doesn't know how to prove a theorem. Usually, SMT solver has some built-in limits, because without them it would loop infinitely. If the limit is reached, SMT solver gives up. The whole point of SMT solvers is to use axioms as little as possible. Instead, it tries to use some specialized algorithms that are really good at solving problems in a given theory. For instance, the minimum function would usually be handled by a special module that deals with uninterpreted functions. Such problems could be then efficiently solved using unification algorithm. The inequalities would usually be solved with simplex algorithm in a module that deals with linear arithmetic. Equalities are handled using congruence closures and unification. Also notice that the less axioms we use, the smaller formulas we obtain, and smaller formulas can be checked more efficiently by SAT solver. However, no matter how much we optimize, there will always be the risk of very long or even infinite computations. That's why, when we try to prove correctness of specification, we have to make a choice. Should we assume that it's true and try to prove it for all possible cases? Or should we rather assume that it's wrong and try to find at least one invalid case? Generally, the latter option is what all SMT solvers go for. Just think about it. Would you rather know that the specification is correct or incorrect? If you decide to check the validity of all models, then you will get results every time there is a mistake. But if the specification is correct, then checking might take a very long time. On the other hand, if you assume it to be wrong and search for the contradiction, then you will find the mistake, if there is any, but you might get stuck when the specification is correct. But if you get stuck, then you can always try to prove it manually with some other tool, or perhaps make the solvers work easier by providing more details. I hope you enjoyed this short video. See you in the next one.